I'm going to go ahead and get started. My name is James. We're going to be talking about electrolytic capacitors. How many people here have ever heard of a capacitor? Great. How many have ever seen a bulged or exploded capacitor? Great, because I realized last night I don't have a single picture of a bulge cap in this presentation. So a common thing I hear is, do you really need to replace electrolytics? And the answer is yes, for a couple of reasons. The number one reason is they can cause damage, like shown in this picture. The electrolyte leaked out and it ate up all the copper under the pads. So then I also hear, well, I opened up my computer or my power supply, all the caps look fine. Also, if they've been in there for 40 years and it's still working, everything's fine. Well, the problem is damage can be hiding in a couple of different ways. This is the most obvious, where after I lifted the cap up, I could see that it had corroded and started eating at the pads. The other thing is all devices will wear out eventually, which I'll get to in just a minute. And then just to be clear, sometimes replacing the caps will fix a wide range of problems. Thing won't power on, good chance there's a shorted cap somewhere. Audio's not working, there's probably electrolytic somewhere that leaked. So it's a good preventative and reactive measure to replace electrolytic caps. For those that may not know what I've done, and to get some street credit, a couple of years ago, I used to live stream retro computer repairs, which led to a project called the Mega 2E. And that's where I took the Mega 2 chip out of a 2GS and built an entire Apple IIe computer around it, which is the little one that I'm holding. The other thing to know about, and I always, I manage a GitHub repo called BitPreserve. And this is a repo where people have redrawn schematics in KiCad. And so there is a long list of computers at this point. The idea is, if you're trying to do a repair or you're doing a recap, instead of reading a fuzzy scanned PDF, you get a nice modern option instead. So I'll show this again at the end, but it's called BitPreserve if you search on GitHub. Okay. Instead of an agenda slide, this is what we're going to cover today. Don't worry about all the details. I'm going to get to those in just a minute. But if you want to download the slides, this one is near the front, and this is most of the stuff that we're going to cover. Okay? So, just so we're on the same page, capacitors are a deceptively complex device. While they only have three components, two terminals, an anode and a cathode, and I still refer to those even if it's non-polarized, and then a dielectric layer. Depending on what those materials are, the characteristics of the capacitor can change. Fundamentally, capacitors are described with this equation where K is the permittivity. You might also call it dielectric constant. Turns out it's not constant. And A is the area that dielectric covers. And so if you look at like a ceramic capacitor versus an aluminum electrolytic, the A on the ceramic is pretty easy. It's the X and Y of the terminals or the plates. For aluminum electrolytics, the foil has a bunch of peaks and valleys. And so it has a massive surface area because there's also a Z direction, which is why aluminum electrolytics tend to have much higher capacitance than ceramics. D, the distance between the plates, means the smaller you make that distance, the more capacitance. And this is why tailend capacitors tend to have more capacitance than anything else, because their dielectric layer are only like 20 angstroms thick. So they're extremely small. And actually, same thing with EDLCs or supercapacitors. Their dielectric are basically one ion, which is why their capacitance is so high. I can worry about that today. So just so you know, there are like 5 major types of capacitors. Today, I am 100% focused on aluminum electrolytic. If you'd like to talk about the other capacitors, I'm a huge capacitor dork, and I will happily talk to you about whatever ones you want. Okay, so let's talk about how an aluminum electrolytic capacitor is formed, or how it's constructed, and then I'll show you what one inside looks like. So the anode foil is aluminum, and then during manufacturing, a oxide layer is grown on top of that foil, which is aluminum trioxide. Another foil for the cathode is also aluminum. And the problem is, if you put those two foils together, they will completely destroy the dielectric, and then you'll just have a short, which will actually be a really lousy resistor. So we put a piece of paper in between to physically isolate them. But now they're also electrically isolated. And the reality is, even though we say this is the anode and this is the cathode is actually this layer of the dielectric. We just have to get away for that layer to be connected to that terminal. And the way we do that is by what do you call it? When you saturating paper with a liquid electrolyte. Now this electrolyte is ionic, it's relatively conductive, but it's also acidic. It's essentially water and glycol. The fact that it's acidic and the fact that there's water in there is two significant things to understand. Because it's acidic, over time, the electrolyte will actually break down the dielectric layer. In fact, it can get very, very small. The good news is when you apply a voltage, just like in manufacturing, the dielectric will draw oxygen from somewhere, in this case, the electrolyte, and it will regrow itself. The downside of this process is, as you pull out that oxygen, you're releasing hydrogen from the electrolyte, and that hydrogen has to go somewhere. If this process happens too quickly, you get a whole lot of pressure, and then that's when the can will pop. If it happens relatively slow, the rubber seal on the capacitors are designed to allow hydrogen to permeate through them over time, because this is an expected process. Okay, I'm going to come back to why that matters in just a minute. Let's look at what these things actually look like. These are some pictures from my friend Derek, who took one apart. At this point, the can has been cut away, so we're just looking at the roll and the foil. As he unrolls it, you can see that there is a aluminum foil and then paper that's been soaked with electrolyte. I wanted to show that because a lot of times when we talk about wet electrolytic capacitors, people imagine that they're water, like it's like you could like slosh it around. The reality is it's more like a paste, and so it's there. It is kind of wet, but it's not like you're filled with water. This is just a picture of the terminal connections. So when you think about that lead that's coming out of the cap, it's welded to one of the pieces of the foil. And then this is just another picture to show that once he's taken the strip out, you have one of the foils, the paper, and then the other foil. Okay, pretty straightforward, right? So he took his time and he did his video that way. I did my video this way. I found my method to be much more fun. However, I couldn't really show you much after that. So, and by the way, to do that, I just I did a reverse voltage of like 4 times the rated voltage and allowed it to draw an amp, so they go real quick. But don't worry, I had a super advanced protection shield in the case of a Sterilite container, so everyone was safe. All right. So I mentioned that electrolyte, and the thing is you have to understand all components wear out eventually. So you have early life failures, which you hope the manufacturer has figured out a way to screen out. Then you have the normal operational life, and then eventually you start to get wear out failures. And for an electrolytic capacitor, that means that the electrolyte has started to either dry out or it's leaked out. There's a parametric failure, which means the ESR goes up and the leakage current becomes out of spec. Leakage current is when it is the result of the dielectric regrowing itself, because the capacitor is drawing current to grow the dielectric. So that's where that leakage current comes from. Anytime you hook up if you just put a electrolytic capacitor on a power supply with, say, like 5 milliamps and watch the current will start relatively high and it'll taper off because it's charged up. Any dielectric healing that has to happen happens, and then you go into just basically ionic dissolution. Now, catastrophic failure is where there's a short between the terminals, which inside the capacitor, not outside, but inside the capacitor, is extremely rare. The paper keeps them really well separated. What's more likely to happen is that because of leakage, the amount of hydrogen that's getting released is increased, there's high pressure, and then the can explodes. It's essentially what happened when I reversed the voltage on that video clip. Too much hydrogen got generated and the cap blew. Or because of self-heating, as the ESR goes up and you run the, say, computer, the capacitor itself gets hot. When it gets hot, hydrogen gets generated and then the can pops, okay? So This is why the catastrophic failure and the wear out is why I get concerned when people say, oh, well, if the caps have been in there for 40 years and it's still working, they're going to be fine. That's not the case. Eventually, they're going to fail. Okay, so once they do fail, how do we pick out replacements? Has anyone ever gone to a distributor's website and tried to buy a capacitor before? And was it easy since there's only like 4 options? Yeah. So, yeah, so let's talk about that. Now, I think most people, when they think of capacitor replacement, the first thing they go to is the capacitance and voltage values. Really critical things. We'll talk a little bit more about those in a minute. But the next thing I want to talk about, because when you start comparing types of capacitors, one that will stick out is their endurance or lifetime. Most commercial grade electrolytic capacitors are only rated for 1,000 hours of operation. And you're going to say, oh my God, how's that possible? Everything I have in my house must be dying. Well, that's 1,000 hours at the rated temperature, at the rated voltage, and that's only to guarantee that the component will not reach parametric failure. It doesn't mean that 1,000 hours and 1 minute it explodes. It just means that after 1,000 hours, the leakage and ESR will be within spec. It also means that the capacitance will be in spec, but if the capacitance is out of spec, the other two are going to be wrong anyway. So that's what, when we talk about endurance, that's actually what we're looking at. Does the capacitance change? Does the dissipation factor, which is essentially ESR, and then is leakage within a certain value? So here's the really cool thing. You can cheat and make that number much bigger just by derating the capacitor. And the easiest is derating by temperature. For every 10 degrees you move away from the rated temperature, you double the life. So for example, if we have a 105 degree C rated cap that has a 1,000 hour lifetime rating, at 55 C, so slightly above ambient, so most of the temperatures that will be inside of a vintage computer, it turns into 32,000 hours. And the thing again to remember is all that means is for 32,000 hours while it's on, the cap will be within spec. Okay? It doesn't mean that it fails. It just means by this point the ESR could be as much as twice as high. The leakage might be a little bit higher, but it doesn't mean it's complete failure yet. Parametrically, it's failed, but it's still operational. The other thing, in case somebody doesn't realize it, 1,000 hours is roughly a month. It's like 42 days, but I just consider it a month. So if you wanted to do easy math. Now, the other derate you can do is, well, let me ask this question. Has anyone ever heard you should always double the rated voltage for a capacitor? Yeah. Does anyone know why? It actually, the actual answer is it depends on the dielectric type. Each dielectric has a different reason to derate the voltage. In the case of aluminum electrolytics, the primary reason you derate is you do get a little more life out of it. However, it's not quite as clean as voltage. It depends on the case size and the type of electrolyte. But in general, if you derate, you get a benefit up to about 30% of the rated voltage. Meaning if it's rated for 10 volts and you apply less than 7 volts, you will get extended life out of the cap. But it's not as simple as saying for every X percent you get X life out of it. You just get longer life out of it. Okay. Okay. Now it's time for the data heavy section of this talk. This is the same chart I showed you before. This is the order that I go through when I want to replace a capacitor. Again, I'm a capacitor nerd, so I buy all of my replacements myself. I don't use kits. I don't have anything against kits. I just like to pick out the highest quality capacitor that I can. So when you look at capacitance value, for most electrolytics in vintage hardware, the value is not highly critical. You do want at least as much as was originally in the circuit, but you can usually go higher. If you didn't know, most components come in what are called E steps. So there's like E9, E12, E24, and that's where you have values like 10, 12, 15, 18, 39, 47. So that's why there is like a 4.7, 47, 470, 4,700 microfarads or ohms. That's where those values come from. The reason I'm mentioning it is if you're on a tier 1 distributor site looking for a 330 microfarad capacitor, make sure you search for the values between 330 and 390, because sometimes they get stuck with values that are not on the E steps, and nobody buys them because they search for 330 or 390. And so you might find a really good deal on a 350 microfarad capacitor, which will work just fine. In terms of the rated voltage, higher rated voltage is always better. I tend to try to get a higher rated voltage simply because I want longer shelf life. The dielectric I forgot to mention this, when the dielectric is grown, it's grown at some multiplier of the rated voltage. It's either like 2 or 4 times. So like a 25 volt capacitor will be grown with a 100 volt dielectric. And so that means that a 50 volt capacitor will be grown at a 200 volt dielectric, which means it can sit on the shelf and let the dielectric layer get eaten away for longer. So when it comes to rated voltage, always go for higher, the same as, or try to go at least one step higher. Dimensions are they don't seem critical except for the pitch. And the reason I say that is, yeah, you need to measure what the diameter is, and you need to know what the length is so that whatever you buy new is going to fit. Thing is, any modern capacitor is probably going to be smaller than a vintage capacitor. Where you have to pay attention is the pitch, because if you do get a slightly smaller diameter, you might go, for example, from a 7.5 millimeter pitch to a 5 millimeter pitch. And you really don't want to be bending the leads on putting stress on those leads, because it ruins the seal and it can damage the dielectric when you're bending them around. So always measure the pitch. And what I tend to do is I measure the pitch of the holes on the PCB, not the capacitor itself. And in a second, I'm going to show you that I forget to do this myself, but I still want to mention it. We just talked about temperature. My goal is I always try to get a 105 or 125 rated cap, because I want the life D rate that comes along with it. The other thing, if you go a step higher in voltage and you go 105 or 125, especially if the caps were originally rated for 85, they will be closer to the vintage size capacitor, which also means that their impedance will probably be more similar to the original capacitors. Now, in supplies like, say, like the Commodore 64 that uses all linear supplies, or most of them are linear, the impedance really doesn't matter all that much, but for the switching supplies, impedance can play a role. However, of all the recaps I've done, I've never run into a problem where a supply has gone unstable because of a modern cap, unless I put the wrong value in. So the reason I wanted to mention impedance is because you will sometimes see that on a distributor's website. Some will list impedance information for the cap. The reality is, if you're not going to know what the impedance of the original cap was. And so if you see two that are similar, just get the one that has the lower impedance, because it means it can handle more ripple current. So is it common for newer cap or modern caps to have a lower loss tangent compared to vintage caps? I'd say in general, yes, but I don't have data that says that. Yeah. Yeah, so the question came from switching regulators. Real quick, what I'll say is switching regulators are very sensitive to the impedance of the passive components that are attached to it. We worry about, oh, is this the right capacitance or is this the right inductance? But the ESR and ESL of the capacitor might actually affect the control loop of the switching regulator. And that's where I was trying to get to, is that on paper, yeah, it could be an issue, but in practice, I've never actually I've never done a recap and then saw the power supply become unstable. So in general, it's going to be fine, but yeah. Yeah, something to be vigilant about, because if you are working with a switch mode power supply, make sure you kind of test it. Ideally, if you have an oscilloscope, you should check its output to make sure that it's working correctly. But I also wouldn't fret too much about it, because in practice, I haven't run into an issue. So on the substitution, so for the substitution, can you go plus or minus 1? I would only go up. I wouldn't go down. Yeah. Yeah, for me personally, I try to only go one step higher and no more. Just because unless unless I have a really good understanding of the circuit, I'd rather stick really close to the values. But 1 up is, I mean, with the tolerance values, and modern capacitors are much tighter in tolerance, so they're going to be much closer to the rated value anyway. So going up by 1 is not going to be an issue. Yeah, there's room if you don't. In fact, at this point in my life, if it's 100 microfarads, it's pretty much going to be a 120 or a 150 because I've got boatloads of those. Yep. All right, I want to bring up one more, with the exception of, we were just talking about going up and down on step sizes. Cost. If I'm happy with everything else on this chart, and then there's 2 options and one is cheaper, I'll go with the cheaper one. Otherwise, I really don't care, because why am I going to spend a lot of time trying to save 25 cents on a capacitor that's going into a computer I've spent $300 on? The main reason I bring this up is because this chart is not how I would pick electrolytics for a new design. This is how I pick it for repairing vintage electronics. Okay. In terms of how I actually go through the process as I'm removing the caps, I record things. Now I'm super fancy and do it in a spreadsheet. I started with just paper and then a text editor, and now I've made a spreadsheet where I clearly forgot to add the pitch, but you know, live and learn. URL on the bottom, vald.ee/model 100-caps if you want to actually get a copy of the spreadsheet. Basically, I just look at where the designators. Let me come over here because I'm pointing to things that nobody can see. I do the designators, the capacitance value, voltage, the size, and then, like I said, I should have done the pitch on all of these, but I didn't, and then any special notes. What you'll notice here is I don't record the rated temperature because I sort of don't care. I'm always going to get the highest rated temperature I can get anyway. So now, and then once I find the replacements, I mark them over there. I do want to note something. Notice that these have NP next to them. I'm going to talk about what that means in just a minute. And then just as a tip that it took me too long to learn, when I get the caps from my distributor, I don't care, even if I put into their order system what the designator is, I always write down the cap, the voltage, and the designator for the current project. Because when you start recapping, it is really frustrating to look at little print and try to figure out which cap is which. It's much easier just to find the bag that has C105 in it. Did you have a question? Oh, pitch is the, so what is pitch? Pitch is the distance between the pins. Yeah, so like that, what I'm saying, and that's because as you go into different diameter sizes, the pitches typically step up, but sometimes within a diameter, there are 2 pitches available. Okay, got a couple of weird types of electrolytics I want to cover. So I said that chart showed NP, which stood for non-polarized, which are also called bipolar. These are fun little caps. They look like a traditional aluminum electrolytic, but you will not find a cathode marker anywhere on them. And that's because they are non-polarized. I've run into these in really 2 places in vintage computers. One is Apple monitors have a 4 microfarad bipolar cap. And then these came out of a TRS 80 Model 100 on the RS-232 lines. The way you get to a bipolar cap is you take 2 electrolytics and you tie them together at their cathode. Then their anodes become non-polarized connections. The way that those caps I just showed you got made is that their anode foil actually has margin right down the middle of it, so it effectively creates 2 caps in series. The reason I mention that is because if you can't find a bipolar cap, they're getting harder and harder to find. You can make your own, or I would probably use like a C0G ceramic if you can get enough capacitance, or a film capacitor will work as well. Okay, I want to mention another type of electrolytics or aluminum capacitors, which are called aluminum polymers. Sometimes they're also called solid. I think they have another name, it's escaping me. The idea is it's the same construction, but instead of that wet electrolyte, it is a solid conductive plastic material called PEDOT, P-E-D-O-T. The cool thing about it is it will have an order of magnitude less ESR for the same capacitance, voltage, and case. So if a traditional electrolytic is, say, 1 ohm of ESR, the polymer will generally be 0.1 ohms. They also don't suffer from ever exploding because there's nothing to explode inside of it. So when you look at them, if the cap has a completely flat top, it's probably a polymer. If it has a stamp for stress, it's a wet electrolytic. Even though these are solid, they also have a wear out mechanism. Over time, the polymer will absorb moisture, and as it absorbs moisture, the polymer gets oxidized and its ESR goes up. Now, its operational lifetime is about 1 order of magnitude more than a traditional electrolytic, but it will eventually wear out. The good news is when it wears out, it's not going to cause any damage to the whatever it's in. It will just stop working, or the cap won't perform as expected. Yeah, so I just wanted to mention those. Early in my recapping experiences, I was replacing everything with polymers, and over time, I've stopped doing it because they are significantly more expensive. There are also a lot fewer options available, and so it just kind of, it's like, okay, I'm just going to stick with high quality, high temperature electrolytics. I mentioned this a second ago, so in CRTs, and especially in Apple CRTs, there's this funky bipolar capacitor that's it's exactly 4 microfarads. There is not a modern replacement for that. All of the modern bipolars are orders of magnitude smaller, so there is no way they have the right parasitics or ripple current carrying capability for that part of the circuit. So for this bipolar, if you're doing a CRT, you see a bipolar capacitor, you want to replace it, look for a film capacitor to replace it instead of a aluminum electrolytic. So this is a look at a Macintosh LC where the sound has stopped working, and it's not clear to me what corrosion has happened, but there's a ton of corrosion everywhere, which I actually think are these small can electrolytics have leaked. I think that for 2 reasons. 1, I see evidence of it, and 2, once I replace those, sound started working again. This brings me to point out that when you are looking at recapping in terms of priorities, number 1, anything that's bulging or leaked, that's clearly got to go. And then number 2 is the smallest capacitors tend to have the most aggressive electrolyte. It's the most acidic, and the seals are not manufactured as well as larger cans. And so in terms of the order that I replace, I look for anything that's clearly damaged, and then I replace the smallest electrolytics, physically smallest electrolytics first, and then get to the big ones later. As an example, this is a Commodore 64. I've probably done 20 C64s. I have never found any of these 3 axials to be parametrically failed. They're all decently okay. None of them have leaked. I have found the smaller electrolytics, which are surrounding the VIC cage. Occasionally I find one of those that has gone bad, just as an example. Now, I show this example because, has anyone tried to buy a really large can axial capacitor recently? Yeah, the key word in that question was try, because I don't think, especially this one, there is no modern equivalent for this. That I'm pretty sure one of these 3 I know there's no modern equivalent for. So I came up with an adapter that I called a BAC, and I'll let you try to figure out what big something capacitor means. It's basically a surface mount carrier that you can put surface mount electrolytics on. You cut out the axial, and then the leads just attach to this board. If anyone is interested in some of these, I have a massive pile of them, because at one point I was going to sell them, and that was like 5 years ago. So if you are doing recaps on a C64 and you want to replace the axials with something modern, then feel free to come up and grab the boards. Okay, I wanted to show this one only because I think, well, like I said, I'm a capacitor nerd. So this is the inside of a Game Gear. And in this picture, I'm removing one of these surface mount capacitors. Now, in this picture, I've highlighted these caps. And if you look at them, they almost look like surface mount tantalums. However, this was a consumer device in the 90s, and tantalums were not something that you could afford to put into such a device. And so I was like, what are these caps? Well, the first clue is almost all of these caps have leaked in every Game Gear that I have recapped. So this is what the capacitor looks like up close. What I realized is it has a really thin plastic epoxy. And if you break it off, inside is a tiny can electrolytic, which is why I said the first clue is that they all leaked. Again, the smallest cans tend to leak before any of the larger capacitors. Like I said, more aggressive electrolyte and the seals just don't work as well. If you want to see some of these, I have some. I brought some that haven't been cracked open if you want the joy of cracking it open to see what the can looks like. Okay, to close up, I just wanted to mention a handful of tools that I found helpful when doing repair work with or recapping computers. First one is if you're going to do more than one project, consider investing into a pump-based solder sucker. These basically have a soldering iron tip to heat up the solder, and then they suck out the solder from the hole. I have this super fancy Weller, which works great, but it's also like $1,500. There are $100 to $200 options that work just as good, especially for recapping projects. They work really well. You get very clean holes. It's much easier to get the caps out. Highly recommend them. If you still want to use a manual solder sucker, please don't waste money on that $10 blue one that doesn't work. I actually don't know what the model number is. I think it's like SSO2, but if you search for Japanese solder sucker, you'll find people that sell this one, and this one works exceptionally well. I'm very happy with it. I just don't like using it. What about solder wick? Oh yeah, you gotta have solder wick too. So if you only have solder wick, then what you'll probably want to do is kind of heat up the joint and then try to pull it out a little bit at a time. You'll probably never get the lead completely off, but you'll definitely want solder wick, even if you have the solder sucker, to clean up afterwards. Highly recommend. Yeah. And get high quality solder wick. Stop buying it on Ali and Amazon. You want to get MG Chemicals or I forgot who makes solder wick, which is actually a trade name. Get it from a real company because it will have better flux. It'll be better weave. It'll just work better. Bench power supply with constant current capability is really handy for either testing the leakage of a capacitor or reforming a capacitor. Basically, the way you do it is set the voltage to whatever level you want to reform or test at, and then set the current limit to something reasonable, like a couple hundred milliamps. I mean, if you're testing leakage, you can let it draw a few milliamps, but if the cap's drawing like a milliamp, it's probably outside of its leakage spec anyway. But the idea is to test leakage is you just leave it sitting there for a couple of minutes, and you should see the leakage current constantly go down, and it should get down within whatever the specified level is. Like I said, if it's drawing a ton of current, then it's probably out of spec. If you leave it sitting there in constant current mode on the power supply, eventually the dielectric will reform itself. So that's what reforming the capacitor is. It's basically that's the same. It's the same process to figure out both. For testing capacitors, you really want something that can test both the capacitance and the ESR. So there are LCR meters. My personal favorite is this ESR 70 from Peak. The downside of this one is it costs $120. So I recognize that might be more than some people want to spend, but it works really, really well. They claim it works in circuit. I don't believe in circuit measurements, so I don't care whether they think it does or not. The key is you do want something that measures ESR because like a DMM will only measure capacitance. The way that this ESR meter works, and most LCRs work, is they put on an AC signal to basically create an AC voltage divider, and that voltage divider tells you what the ESR of the capacitor is, because you're basically measuring, you're basically measuring the reactance, and then from there you can back out the ESR. And then after they do that, they apply a constant current and measure how long it takes to rise to a certain voltage point. And then based on that, they can back out what the capacitance is. And that's actually the measurement that your DMM is doing. It's just applying a current and then measuring how long it takes to charge to a certain amount. If anyone's interested in seeing this, I have one of these with me. I can show it to you. And then the other one that I really like, and didn't really get into it in this talk, but anytime I talk about caps, the Analog Discovery 2 and 3, I have a 2. I was loaned a 3 for a video. They have an impedance adapter, which is basically just a couple of relays and resistors to make the measurements easier. But what's really fun about it is you can plot both the impedance and capacitance curves of a given capacitor. If you're looking at a vintage capacitor and you plot this impedance curve and you see any massive funny spikes, you can pretty much guess that the cap, there's something wrong with the cap. This is nice for, well, I won't get into that. All right, a couple of resources I'll tell you about. I've got a whole bunch of capacitor videos. I talk a lot about them. I was a FAE and then technical expert at Chemet for almost a decade. So I've talked a lot about different types of caps if you want to go learn more about those. As I mentioned in the beginning, I do have the bit preserve GitHub repo. I use it when I'm recapping because it's nice to be able to match what I'm seeing on the PCB and the values that are in the schematics. All right, any other questions? Can you, yeah, please, thank you.
So, okay. So, one of the things that I've been told, and this is just what I've been told, sometimes on like Facebook and groups like that, is that recapping isn't really a thing; it's a myth, and that it sometimes, unless you see them like visibly leaking, if you go into a recap, you can introduce more issues. Like for example, one time I had a Yamaha DX7. It had a bunch of issues with it, so I replaced every capacitor. It had audio issues, and it still didn't fix anything. And none of those capacitors were visibly leaking.
Okay, so. Yeah, I hear this all the time is, well, if it's not broke, don't fix it. I fundamentally disagree with that because I know at some point those capacitors will fail and you don't want them to cause damage when they go. Something else, I should have said this at the very beginning. Please do not recap a vintage piece of electronics as your first soldering project, okay? There is a lot of technique that you have to learn to properly remove the capacitors, or any device for that matter. If that's been battery bombed or you got a bunch of issues, please practice on that. Do not make it a soldering project.
So just to clarify on non-polarized caps, can you make one by just putting the anodes of two outer capacitors together?
The cathodes.
The cathodes, okay.
Yeah, you tie the cathodes together, then the anodes will become.
And then you'd have to calculate the capacitance so you arrive at the same value.
Yeah, 2 points. One is I would measure the capacitors and try to find two caps that measure close to each other. You want them to be, for the most part, you want them to be balanced.
Yep.
And then it's going to be, since they're in series, it's going to be the half of whatever the value is.
Yeah. I work on a lot of CRTs around kind of 79, 80, 81, and they all have that big non-polar cap.
Yeah, so for that one, I actually recommend looking for a film-based cap instead.
Okay, thanks.
Yep.
Do you keep a stock of either common or uncommon values in a kit, or do you always order fresh for whatever you're doing, or is it a combination?
It depends on who I have to answer to. I would say for the first 3 or 4 different devices I recapped, I bought brand new caps no matter what. At this point, I have a massive Stanley container that has about 50 values in it. And so in general, I'll try to look in that first. However, a lot of times I just sort of get carried away and just buy new ones anyway.
Hi, 2 questions. First, we probably know what the short answer is. What is your longer answer regarding reforming vintage caps? And the second question was, have you seen, as I've heard before, that caps that were made many years ago are significantly better, have longer life than current ones?
Okay. For the first one, for reforming, there is a caveat. If it is old enough that it is oil-filled, which is like 50s era tube radio era capacitors, those tend to reform very, very well. There's plenty of ions available to reform the dielectric. For anything that's using more of the water glycol style electrolyte, if you're in a pinch, I would maybe reform it to see if it solves an issue, but I wouldn't use it long term because reforming is depleting the dielectric. It's part of the process. That's where it's getting the oxygen from. Regarding our caps made maybe like 10, 15 years ago, better than the ones today, that's questionable. I don't know. I strongly feel if you buy tier 1 capacitors, so for electrolytics, I tend to stick to Panasonic, Nichicon, UCC, Cornell Dubilier if I need something larger. They're going to be formed with high purity aluminum. The electrolyte will be well tested and they'll be well matched together. Once you get away from those brands, I would argue that older caps may actually be better than those.
Thanks.
Yeah. I thought you were going to ask about the capacitor plug thing, which I actually think a lot of capacitor failures get blamed on the capacitor plug of the 90s. While it is true, it was actually limited to like only a couple of factories. It's just that by that point, everybody's standards were getting lacking, so lots of failures were occurring. But yeah, I mean, anything made before 2000, I would replace the caps. That's just how I work.
Do you feel like the various seals or the other parts of a capacitor that when they are unpowered or basically unused in a circuit for a long period of time, what's their, like, I guess, most common failure point, and what kind of factors affect that other than the voltage actually applied in the electricity?
Okay. I think sitting steady state, I don't think anything about the construction of the cap is actually really, I don't think there's much of an issue. As long as the seal is not being stressed. So that's like if you bend the leads to put them into something, you're stressing the seal, and now you're causing mechanical stress that wasn't accounted for. When I say that the electrolyte is acidic, I mean it's like a 6 on the scale. It's not like a 1 or a 2. That's the acid way, right? It's not the other way, yeah. And so it's acidic enough to break down the dielectric, and it probably has an effect on the seal, but only on really poorly made seals does it actually leak out. That's where you see the leaking, that's where the plague came from. But if it's well made, it's probably not going to cause a problem. Sitting unpowered, the biggest issue is that the electrolyte is getting depleted. I mean, if it's going to fail, it's failing because of that. Not the electrolyte, the dielectric. Yeah.
Looking at your charts, the hour ratings and the D rating for temperature, it kind of seems like even if you get a really high rating capacitor and run it at a low temperature, you're not going to approach anywhere near the like 20, 30, 40 years we sometimes see based on this. Is that just a matter of what the manufacturer can guarantee or promise is very different than what might happen, or is there more to it than that?
No, it's exactly that. It's because it's simply the guarantee that after this period of time, you'll be within spec. It's sort of, let me give an analogy that's still related to capacitors. So think about what does rated voltage even mean for a capacitor, especially in electrolytic, because if it's rated for 25 volts, you can apply 50 volts to it for a very long time before it destroys itself, right? So then why is it not rated for 50 volts? Well, the reason it's rated for 25 is because the voltage rating determines how long can the device provide guaranteed specs. And so the same thing on a ceramic capacitor. Those are all rated for 1,000 hours of endurance as well. However, nobody ever talks about replacing those because all the capacitor manufacturer has said is after 1,000 hours, we know that at this voltage and temperature, it'll be fine. The reality is it's going to be fine for 100,000 hours. So yeah, so it just comes down to they're just saying, we know it will be fine up to this point. It really becomes more critical when you're talking about things that are dependent on the parasitics of the device. So like if you're talking about a filter design, that's where it's more critical because then they're going to say, hey, if you're going to put this next to a MOSFET, after 1,000 hours, your filter is going to drift and sound different. Okay. All right, any other questions?
So what brands do you recommend using and what to stay away from?
I won't say which ones to stay away from just because that list is much longer. What I would say is, please, when you're recapping, don't buy parts from the gray market. So that's AliExpress, DigiKey Marketplace, and Amazon. If you search on DigiKey, please exclude the marketplace, and then any brand that they sell is fine. Same with Mauser and Newark. In general, I buy Panasonic, United Chemicon, which is also UCC, Nichicon. I'm sure there's another one in there I'm forgetting about. Rubicon, that's exactly the one I was picturing the logo and I couldn't think of the name. For larger cans, Kemet, Kemet, or Cornell Dubilier, those would all be good. Again, if I didn't name a company, I'm not saying it isn't a good option, but I would say if it's either a Japanese or North American supplier, it's probably fine. Some of the other ones are probably fine as well, but those are the ones I stick to because I know that they take the reliability really seriously. Oh yeah, Illinois Cap, yeah, they'd be fine. I tend to not, they tend to be, I tend to see them more for the larger cans, but yeah, I'll buy them every once in a while. That's why I had the picture of one of them in the comparison slide. Or maybe that was a different slide deck. All right, any other questions? Okay, most of the internet, I'm Bald Engineer, so if you think of something later, feel free to reach out and ask. I'll be walking around the show for a few minutes. Like I said, if you want to come up and see the either the BACs or these tiny cans out of the Game Gear, I've got some of those to take a look at. All right, thanks for the time.